Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Thank you ever so much for joining us today. We appreciate things are a little bit out of the ordinary and people's schedules are all over the place. But for the next hour, we can sit back, relax, enjoy a presentation and a software demonstration in order to find out how engineers, scientists, and other industrial data explorers can process their data, make it accessible and interactive. So we're going to discover how you can better understand and optimize your own chemical processes using powerful interactive visualizations and point and click advanced analytics. So this is a webinar that is brought to you by both Chemistry World and JUMP, which is part of SAS. And this is a statistical discovery software. JUMP are a company we work with a great deal. They are very, very good at finding us fascinating case studies and really interesting people to hear from and to learn a lot more about how to make the best of any work that you do, in this case, looking at chemical processes. So the guest that they have helped us to find today is an industrial data scientist and chemical engineer at advanced materials and specialty chemicals company Solvay, and that is Francisco Navarro. Now he helps to solve challenging optimization and process engineering problems for a wide array of industries around the globe by transforming operations through digital and industrial data analytics. He has a PhD in modeling and simulation, so he's exactly the sort of person who knows how to improve your processes. So we're delighted to have him with us. Before we hand over to him, we're just going to explain a little bit about the GoToWebinar software itself. The big advantage of this over a video or a PDF or just an article is that it allows you to interact. So not only can you see a real-time software demonstration, we will actually be showing you with real, if slightly adjusted data, so there's no special secrets let out. And we'll show you how the software really works, but also you can ask any questions that you like at any point throughout the presentation. So we're going to have a Q&A session towards the end, but if you have any questions at any point, then drop them into the questions box that you'll see in the GoToWebinar software, which is almost certainly a panel on the right-hand side of your screen. So any questions you have, put them in there. We will put them to our guest at the end of the presentation. That's about it for the GoToWebinar software. So the key thing now is for me to hand over. So hopefully the next voice you will hear and the presentation you will see is from Francisco Navarro. So thank you ever so much for joining us, and I hope you enjoy the presentation.
Thank you very much for the introduction. So yeah, today we're going to talk about industrial data science in the chemical industry. And the first thing I want to start with is with our founder in Solvay. Ernest Solvay was saying that from science we derive the progress of mankind, and actually we're going to talk about data science. So data science is it's a science. Okay, we have to not only learning from data, but the part of the scientific method behind. And in a nutshell, the traditional method we have been doing models is we develop the we give some inputs, we have some models from theory, and then we have an output. With a machine learning approach, we have the privilege to have several examples, several inputs and several outputs, and the computer should be able to learn the model and give its data as a result, so we can go back and use it for our purposes. So, you know, this is a very hot topic today, data science in general, but actually in the chemical engineering, process engineering, we have been using a method of machine learning before for years. The only thing is we didn't call it this way. So anytime you were looking at pseudo-empirical correlations to estimate, for example, heat transfer coefficient of a system or things like that, where we have to use part of the physical knowledge and then other part make an adjustment, fitting a regression of those data. This is a supervised machine learning method, but we didn't call it that way. Another thing is, for example, grouping of clustering data. If you are a chemical engineer or process engineer, you will be familiar with these map flows that kind of categorize the system behavior according to, for example, the superficial velocity of the two phases. And in machine learning terminology, this is called unsupervised learning. So you don't have a target in mind. You want to group data together, but we call it flow maps in this case. And last but not least, today the hottest topic ever is the reinforcement learning, with a lot of promises and a lot of applications. And this is basically, in a way, a system where we use these machine learning methods for process control. So with this very brief and fast introduction, I would like to ask the audience, what do you think is stopping you in your experience? So for the industrial application, the use of this machine learning methodology? We're going to ask you a very brief question for you. So you can ask, you will see the poll in a second.
So yes, it's always good to get some feedback early on so we can make sure that everything is tailored as much as possible. So the next thing you should see on your screen will be a poll where you can interact with us. So what is it that's stopping you from getting the most from your data? Is it simply that the cost of generating useful data in the first place is too high, so you're not getting as much data, not as many points, not as many different factors as you'd hope? Are you on the other side of it and you're having so much data that actually you're starting to fail to see the wood through the trees, as it were, and getting lost? The amount of data is increasing too rapidly. Do you have too many different sources, so it needs too much preparation and standardization before you can really start to explore it? Do you just not have buy-in from senior stakeholders? And this can often be a case where some people have done things the way they've done it for so very long that, that they don't necessarily want to start looking into the data too much, as it might question their approaches. Or are you just lacking the statistical skills or the tools, and we'll hear a lot about tools today, that you would need? So we're going to let people vote for this as long as we can give them. So let's have a look and see how many people. Let's give it a little bit longer, I think. So do get your votes in as quickly as you can, and we'll see if we can get to maybe about 75% of you or so before we can close it on. So let's give it another few seconds, and we'll let the last few people vote. So get your votes in there. And let's close the poll and let's see what most people encounter as the real experience. Well, there's an absolute runaway winner of an answer there. It's simply that people don't have the statistical skills or the tools that they need in order to really make the most of their data. Relatively close behind that, data comes from too many sources, and this is a problem in absolutely every industry, that the ways you're trying to understand your data means that it comes in different formats, different standardizations, even simple things like different tags and column names and so on. So it needs too much preparation to realistically be able to get the most of it. Francisco, does this sound familiar to you? Is this the sort of thing that you've seen in your own industry? So right now, I think I am not hearing Francisco. Now, I don't know whether that's because...
Yes,
thank you.
Yes, you can hear me now, yes. So I was saying that this is a great feedback, and this is exactly the 2 points I will demonstrate in this session. How can you gain these skills, or maybe how can you use them, because I think we all have the analytical thinking skills. And then the data source and the connection of data sources is going to be my next 2 slides. So it's a great feedback and we're going to cover these 2 exactly needs in this session.
Excellent. It's reassuring in a way to see that only 3% of the people here today are suffering from that sort of lack of buy-in, the onboarding step from their senior stakeholders. But it's probably worth adding, for the 3% of people who have said that, the sorts of results and visualizations you can get from this sort of software can be a really key tool to really prove the effectiveness of this approach. So I appreciate there's only 3% of you in there, but I think you will still benefit from this a great deal. But thank you ever so much for everybody for filling in the poll. We'll close the poll now and hand back to Francisco for the rest of the presentation.
All right, so I'm going to tell you the story of how we do it in Solvay, and this is something I call the industrial data science workflow. And you see, this is a very simplified workflow, but it points out some of the problems we have seen in our experience doing advanced analytics projects, which in the case of Solvay has been for a few years already. So first of all, we should start with the problem definition. And the first common mistake is to define this problem definition as the business value, which is not the same. So usually business value is clear. So it's with the people in the plant, they know already where is the inefficiencies, where they're losing money. But what is causing that problem is not that clear. So that's they should have an idea, and if we have probably they will be very close to it, but they are not yet ready to understand the full complexity of it. So first of all, try to identify the problem and not to confuse it with the business value. Then we go to the process data. So we have to get a process description of where this data is coming from. We have to make a session of the data discovery, because there will be some sensors or some tags that we will not fully expect to analyze. So we have to discuss with several people in the plant to what they think it's happening. Then we do the data extraction, which is the second pain point was discussed in the survey, and we'll cover that in the next slide. And then we start with the modeling and the visual analytics, right? So this is the first part. We have to always take a look on the data, and we will start to get a process understanding from this visual analytics approach. We will use modeling and a kind of optimization to have this kind of loop. We will get back to the process data, because we will see, oh, something is missing, we have to get the new data, or we are understanding better the problem, and therefore we have to redefine this data extraction and process modeling by itself. The most important part is that at the end, the action taken, it doesn't necessarily to be a model online, because everyone is always thinking on the most complex scenario. We have to tend to be there. We need an analytical platform for that, where we can put either a sub-sensor, where we predict the quality of the production without having to measure it. We look into the maintenance, or we go into the more advanced process optimization online, or even planning or scheduling. But in our experience, since we are in a chemical company, most of the cases we fix sensors, we fix pipes, or we just introduce new operator procedures. And this is an outcome of a data science. Not necessarily having a neural network online is an outcome of data science. And this is a really important aspect that's sometimes mistaken. So in this demonstration, we will see how to go through the whole process. We will start with decision model trees. We will start with we will do a neural network. We will see interactive models to understand better and how to recommend next actions. So about the pain point in the industrial domain, we usually have a lot of sensors. We call them tags because they're literally tags hanging in the plant near to the sensor. And these tags are sent to the control room through the control system. So the operators are looking at monitoring at the values and making sure that the control in place works. We have historians, and this is the big data set in their plants. So we have operational historians. So we record every single data point and we put it there for future needs, which is often what the process engineers look at their laptops, and then people like me come to the plant or ask for the data to get this big data set and start to do analytics. So the main problem we have faced in the beginning was that this big data extraction and connection to different databases was always a problem, was always a delay for our fast and the workflow I was showing before. So today we're going to show a tool, which is Jump, which is able to directly connect to the databases. And here you have in the bottom line the interface we develop internally to connect directly to all of our servers in the plant. And by demand, you will select the tag or the sensor name. You have a search filter. You will get the values you want. You will drag them to the data table. You will select the time you are interested in, the kind of aggregation interpolation method, and then you will click, and then you will have your data ready. I have to emphasize this is super obvious, but having this direct access from the analytical tool to the database it's a huge deal for everyone, because therefore you don't need to do programming, or you don't need to do any data preparation just to prepare a table. So even the process engineers, any person interested can have access to this huge data set in an interactive way. So with this introduction, I think we have enough slides. It's a moment to start to see the interaction I'm talking about. So for that, I'm going to use JUMP. JUMP is a statistical software. At first glance, looks like Excel, but don't be fooled. It's nothing related to Excel, because the main difference will be the way you have the data. The data in JUMP should be in something called tidy data set. So for the purpose of this talk, a data set is simply, you will have per column one variable. So we have our date, our yield, and organic content, temperature. Per column we have each of the variables, and per row we have a sample time and a measurement of that variable. So I have to emphasize that this is not like Excel, so I cannot create here like a specific formula that it will be only in this cell. If I want to create a formula, as we will see, it will be applied to the whole column, and it will have a new column on the right. Likewise, if I go to the bottom, there will not be missing lines there. So it's said that there are only one way to have a tidy data set, but there are many ways to have a messy data set. So the purpose, and this has several advantages that we will see. So again, this data set is ready to use, and this came directly from the add-in we developed, and this is a huge deal. Why? Because the moment we have this data set ready, anyone can start to visualize data. So I'm going to open the graph builder of JUMP. I will just put the date as an X variable and then my yield here, and you can see that I can make this time series plot in a few clicks, and this is fully interactive. So if I select the beginning of my time series, the beginning of my data set will be highlighted. And if I select the end, it will be at the end of the bottom highlight. So for example, I can add other information. I want to see the yield, I want to see the flow and the temperature. And I can, as simple as that, see all of my trends. If I'm happy with this, I can always click in done. I can always as well do a filter, which is something interesting. So for example, if I want to filter by the organic content of my data set, I just can drag and drop. I see right there the distribution of my data set, and I start to clean the database on the organic content. I can also do what is called column switcher. So for example, let's say I want to iterate through my temperature. So I will just, for example, here I will just iterate through all my temperatures in my data set. So I will just select them. Some chosen the way analysis, so they will remove. And then I just like that, I can, you see in the bottom graph, I just changing the data set as I am clicking in my keyboard. This seems super obvious, but actually doing this kind of quick visualizations of all of my trends, it's really something that can be very complicated if you don't have a visualization tool like this one. So these are very simple trends. And let's go now back to the problem. So in this data set, I have a yield, which is what I care, and this is distillation column. So I have a bunch of temperature sensors, which I can see here. I have pressure sensors, I have a vapor pressure, I have flows. So the problem is, as I show you in my yield, I have I have certain variability. And for the moment, and at the end I will get back to this, you can see that the dates, it's every two days, 3 days, I have a new sample. So we have to know that this data set was sampled when the system was stable, and that, as you can see, given the time difference we have between these two timestamps, we can assume that the measurements were independent one to each other. This is super important. I will get back to this at the end of the presentation. But for the purpose of the demonstration, let's say we have a data set with variability. So we want to understand why the yield was so much better in these cases or lower in these other cases. Is this due to noise? We are not sure. We want to understand what is happening here. So the first thing you will see people doing is the multivariate method. So you will try to understand every possible interaction between the data sets, something like that. I will just going to open this so you can see all of the interactivity that you have in JUMP. So the moment I highlight data here, I see the data highlighted elsewhere. Okay, so we can see that temperature 3 and temperature 2, for example, they are highly correlated. So this is a collinearity. So probably these two sensors are redundant. But how can we understand better what is happening with the yield with every possible variable? And this is a very, very common problem. And this is the first problem. We got our data, but now suddenly we have so much data to look at. So without being a data scientist, you can do the following. You just go to the menu of analyzing, you go to something called predictor screening, and then I will just say, I care about my yield. This is my response. And I want to understand among my other variables, what is most important. And I will click OK, and in just one click, I suddenly have a figure list with a contribution here. This is kind of magic, but what is actually happening is now I will just say, for the sake of here, I will just say, let's only see these 4 variables in the same plot I did before. So I'm gonna get back to my multivariate method, and I'm gonna put this, I'm gonna remove the date, and I'm gonna put the yield here, back here. So now you can see that I have reduced my data set to the ones that I can see that there is start to be certain correlation. In this and in our industry, unfortunately, most of the times linear correlations are either a consequence of our yield or something that we're measuring together with the yield. So you can see that even with this selection, we start to see something happening here. It's not just random noise. I can put the densities, because there are so much points to look at here. So we can start to see certain patterns here. But this predictor screening has allowed me to reduce the number of variables to look at. In my opinion, there is a better way to look at multivariate data, that is the parallel coordinate plot. So if I put all of my variables here, I will have all of the rows. So here I have the highlighted rows, and how these rows are highlighted in other parts of the data. I can connect this directly in my all the lines together, and I will put my yield so you can see what I'm trying to do here. So I'm going to put also the yield as a size. So here I can visualize what are they, like 5 dimensions in one plot. So now I can start to see that if I really want to understand something, for example, let's go in this part, I see that there is a lot of lines that are lower yield and they are going to the lower flow data set. And if I go to the highest part of my yield, I can see that the flow is also going high here. It's another way to start to look at, but it's still, we can do something much better with this. So what is happening in this visualization? Well, what we're doing here is called like bootstrap forest, bootstrap tree or random forest, but we are doing that in a few clicks. So before going further, you will see that this is a list of contributions. So I see how much is this flow explaining my yield. But the problem every time you do a random forest, and this is very common, is that there is no end here. What is the end? You will have a fascinating discussion with all of your engineers in the room. They will say, I knew this, I didn't know that, but where do you stop looking at this? Where do you actually stop looking at this? What is actually relevant or not? So for doing that, because we want to discriminate what is noise from signal, the best way is to add or no noise into the system. So a very fast way to do that is right-click in yield. We go to we want to introduce random noise. We want to introduce random uniform random noise. We want to introduce a normal random noise, and we actually want to use just the same. We want to shuffle around or target. So what I'm doing is, if we look into the distribution of these columns, what I'm doing is basically, I have my yield here over time, and then you can see that when I'm highlighting some part of the yield, all of the randoms are now highlighted. So I actually have noise. Maybe the best way to look at this, because it's important, is to go back to my plot and put the shuffle of the noise here. So it's the same data set, but completely shuffle around in the time, or the completely noise in the input. So you can see this is, I know this is noise. I know this should not be important. So I'm gonna repeat this screening to help me out understanding what is happening. So I'm gonna go back to predictor screening. In Jump, something super nice is that I can call recall. So I will have the last thing I did pop up again as I leave it there. And I will add now, in addition to my tags, my sensor names, I will add the noise here. I will click OK. And notice there is a parameter that I am highlighting now, is the number of trees. I will click OK. And then I will have a new list. But in this case, I suddenly have the random variable happening here. And as you can understand, if in principle, if this is in this part of the contribution, I can start to assume that everything at least below that contribution is just going to be pure noise. Very well. So we have been doing something interesting here. We have a selection, but it's difficult to see because unfortunately your processes are non-linear, but we have a way to start with a simpler number of terms. So what exactly is happening here with this predictor screen? As I say, this is a bootstrap tree or a random forest. So the first thing to understand what is this is to understand what is a tree. In Jump as well, you can go to predictive modeling and say that I want to do a partition tree. And now I'm gonna just include the variables that I know that are important. I'm just gonna ask the all of this. I'm gonna add flow. You can, just to show you, you can select with this search here directly, or you just can do this automatically with highlighted as they were. But just to show you how these work, I will just add these two here, and I'm gonna click. I'm gonna also add my noise I created before, and I'm gonna, just for the sake of this demonstration, put my yield, and I'm gonna click OK. So right now what I have is a decision tree, and notice that I have to start to split my variable, and I will do this tree dynamically in front of me. So the best way to look at what is happening is you can start to, I'm gonna put the contributions as I do the tree. So you can see that the strongest predictions are, I'm gonna prune this, the strongest prediction are the flow C1 and the temperature one. So I'm gonna add a plot, and I'm gonna create a flow C1 and a temperature one right here. I'm gonna put my yield as a color. So suddenly, I don't know if you can start to see something here, but I'm gonna add some density in the background. So you can see, I'm gonna add first the density and then the colors, so you can see where the data is. I'm gonna smooth this out a little bit, and I'm going to leave it like there, because this is gonna be enough to explain what is happening. So a tree is a model that will start with the average value. So if you don't know anything, the best value will be the average of what you have seen before. And that's exactly how you start the model. So among my data set, the average of my yield was 69. But if I start to see among all of my variables, I will see that if you look into this plot, temperature one has a slightly darker area over here compared to over here. So if I do an average in that area, if I split my data set in two sets, depending on my temperature, I can say that when the temperature is higher or equal to 151, so we are above that line, my yield will be lower, which is exactly what we can see here. From 69 will be 67. If my temperature here is lower than that value, I am in a higher area here, which has more yellow color into it, so the value in average is higher, so I will move to 69.4 to 69.5. Then I do another look into all of the variables, and this is what Jump is doing for me, and says, look, if you now look into the flow C1, which is the variable on the bottom, you actually can see that if you are in this bottom line, this is the first dark area, you wouldn't need to look at that, this tree hasn't grown anymore. We can actually just see that if this is temperature is 315, so it's about here, you will see that the area is also darker compared to the right side. So take a moment and think about this, because I'm having a predictive model which is super easy to understand because it's based on measurements of my flow, that actually we can start to see that and share this with any person in the room. And not only that, but I can actually look into the code of this if you want to see it. So since I'm splitting data based on variables, this is basically a bunch of if and else's here. So we can see here that the prediction of the value will be started from 0, and depending if the temperature is some threshold, they will add certain values to this. So this is how a tree works. But what we are doing is a random forest or a bootstrap tree. And what a bootstrap tree does is this tree several times, but doing a sampling. Why will you say you need to do a sampling? So if I start to do this split, you can see that I see here the uniform noise happening. So as I was showing you in the plot, I can very much explain the yield in a broad way with two inputs only. But the point of random forest is, imagine that this flow is very high. So very, very important. It's always explaining this. And maybe in my data set, I have other things happening, okay? So if I go here back, why in my simple tree I start to see the noise in this third attempt, but here I have a nice distribution of other numbers that I will, other tags that I will see. So the reason why we do this is because if I have a very strong prediction and I always use it to predict, then I will miss other smaller predictions. And the trick here is to repeat several trees, but giving a selection of rows, giving a selection of this each time I do a tree. And therefore, I will have at the end the average of the contributions of my 100 trees I was showing earlier. So at this point, you can start to see that I have a pretty good understanding of my system. Notice that this is a non-linear system because this goes high and down in this direction, this goes high and down. It's not a simple linear relationship between the data set, and it's very, very fast because the way I'm splitting the data is very smart, and also it is not dependent on the units of my measurements because it just splits based on each independent measurement. So it's a very powerful method to screen and to do simple models that I can deploy wherever I want. You might ask, what is the improvement of this model? So I'm gonna remove my random noise here in my model. So you can see that my error square is 0.49, and I can actually see the profiler. And I will talk about profiler later. Maybe I can actually see the plot versus the predicted plot. Okay, I will remove this for a moment. So I can start to see there is a very simple way to explain my yield. And maybe at this point is a moment to ask again, what do you think is the problem when you start to do these models in reality? You have your data. What do you think in your experience? What is stopping you from doing that? So I think we're ready for the next poll.
Thank you very much. It's really fascinating to see not only just jump in action, but actually how quickly it can generate some of those visualizations as well. But let's move on to our second poll of today's webinar. So you'll all have to sit forward again, grab your mice, and does your data tend to have any of the following issues? And you can tick more than one, so we should see more than 100% for this. Do you have missing cells or incomplete data, just gaps in your data sets that need to be addressed? Do you have some data points that are outliers, that are far and away from what you might predict from the other data that you've seen? Do you have correlated predictors? These are simultaneously varying inputs, so they can be a real issue to deal with statistically. Or actually, is all of your data perfect and you find you have none of these sorts of issues? The issues maybe you have elsewhere in collecting or that sort of thing. But once you've got a data set, you know that you can trust it, and it is absolutely solid. Now, about half of you have voted so far, so I'm going to keep this going for just a little while. But actually, while you're voting on that, there's a question that's come in from Geordie, who asked whether you could recommend any literature on the subject. Francisco, I'll come to you in just a sec for that. But in terms of JMP itself, there are plentiful resources on jump.com. There's a really strong community there. Phil Kay, who regularly does webinars with Chemistry World about JMP and how to make the best of it, has done an excellent series of blogs on there as well. There's videos and other resources. So if it's JMP itself and not just the statistical techniques, then the resources available on jump.com are excellent. Francisco, are there any other resources you would recommend for somebody who is looking to make the most of this sort of technique?
So I think the recommendation is right, because one of the big differences with JMP and two other advanced analytics tools is that this is a tool for scientists and engineers. So they have a really good resources in their website to start with this, and many examples that can be applied to not only advanced analytics, but other branches of statistics and visual analytics. So I think that's a good recommendation in general for every engineer or scientist in the room.
They've been really good at making sure that they use genuine and applicable case studies as well. So possibly if you were to look into the pure statistical literature onto how to do this, it might be a little bit academic, a little bit divorced from reality, whereas JMP make a point of doing things like this webinar where we do actually bring in the real people who genuinely use this and look at near enough real data sets. So it's a really good resource. But that's probably enough promotion of their website from me. And I think enough of you have voted now, so let's close down this poll and let's see. Well, there we go. So it's very good that so many of you, 12% of you, tend not to have these common problems, but that's a fairly even spread for the rest of it. Francisco, is this what you'd expect to see in real life data sets?
Oh, yeah. This is actually, we have all of them. So exactly what is happening here. We have missing values or incomplete data. We have outliers, so we have correlated predictions one to the other. And this is exactly what I'm going to cover in the next point. So one thing I want to mention is the use of relevant data is super important to understand what is the value you can provide in your company or even academically. And remember as well that I started saying that we've been doing data science in the past, but we will call it in a different way. So with these two concepts, let's go back to the problems looking at data. But relevant data sets are important to learn. And what you know already from your traditional methods, you can use it here. That's gonna be my next topic. So
okay,
let me know when I'm ready to share.
Well, yeah, we'll close down the poll results. Thank you ever so much to everybody for engaging with the poll. There's some really good, actually quite reassuring that hopefully you're getting a lot from this webinar and we're teaching you the right sorts of things. So we'll hand back to a further presentation, and we've still got plenty of time for you to get questions in. So we've had a few good ones in already, but do get them into that questions box and we'll put them to Francisco at the end.
Okay, so very quickly, when you are in a tree here in JMP, you can actually start to talk about validation, which I will cover at the end. But I can do a k-fold cross validation. In this case, it's going to be a random selection in the scaffold, and now suddenly I have a go button here. So I will now have a much more complicated tree that has been with a validation in a k-fold manner. But you can start to see again that the noise is happening here. So I'm actually not adding much more info. I am adding significantly more splits using temperature and flow, but I'm actually having the random uniform and random noise. So a nice way to move from here is to start to prune your tree until you remove all of these different noise factors. And now I have a little bit more complicated tree that can explain better my model. So I can show the nice visualization of that I said before. This is the partition tree I was showing, one tree here, which is in the two values, only temperature and flow one. So with that tree cover, let's go back to this one here, because first of all, there is a lot of multicollinearity in this data set, as expected in any process, because we have things that are redundant. So if I go back to the multivariate method, the multivariate here, and I can put these variables here, you can start to see that these two are highly correlated, so they're basically the same. And there is also something funny here between this temperature 1 and temperature 3 happening. So in data science, this is very common, having multicollinearity. And what we usually do here is either a variable reduction, so using kind of principal components, if these things are linear, or more interestingly, it's called like penalized methods. So we can you can think about in these two temperatures, if they're basically the same, at the end what I want is the average of these two, because they're saying the same. I don't necessarily need to select one tag or the other. So for multicollinearity, do you have penalized methods? I will cover those when I'm going into the neural network. For D3, you can see that the if I go back to my yield plot, you can see here that actually it looks quite noisy, right? So the trees are very robust to this because they split the data just based on the distribution. So if you have a very far away outlier, which I don't have here, but imagine you have a very far outlier, I will split the data here and I will just assume the rest of the points in the same bucket. So that's very powerful to deal with the real bad outliers. But before saying, okay, I need to clean this out, I need to do, you can do this actually as well in JUMP. You can go to explore outliers. I can just go to my yield and say I want to do a quantile method to select all of the what I assume are the outliers. Sorry. So I'm going to go back here and select this. So this what we will do is select me the quantiles that are in the top and the bottom of them. But before doing that, let's think again. So, and this is a very common mistake as well. So this is the yield over the time, over the periods of years, okay? But in my plant, I don't care about the forecast of this as much as I care to explain what happened from my yield to go from here to here. Because maybe this is not noise. Maybe it's actually what I care. What happened that explain my yield here and there. So before going to the cleaning, use these robust methods in the trees or random forest or bootstrap trees, whatever you want to call them, to really help you understanding what is happening, what is missing here. So for that, since things are changing in what I care now is how things are changing in my yield. What I can do is just to say, how can I explain the yield based on changes in my data? So for doing that, I can just select any variable here and I right click and say, look, I want to say go and look at the difference in time. Okay. And I will create a plot which will be the difference, what this time, the absolute difference between two consecutive points to try to explain that. So for the second time, I'm just going to delete this one. I'm going to have, I'm going to repeat this operation, and I'm going to say this. I'm going to repeat the predictor screening, but now I'm going to add the difference of over my yield, the difference of all of my measurements. And you can do that right all at the same time. You can right click new formula column and then go to the when you click here, you will have this n times 2 with the number of selections. And think, you see, you can actually transform, you can do logarithmic scales, because as we know, logarithmic scales help to linearize the systems. We can combine this because maybe it's a product, maybe it's the pressure, so I want to calculate the square root of the pressure, because that linearizes as well the system. So we can create as many features as we want, but here only with the time difference, and suddenly have a difference of pressure being not in the list, but on the top of the list explaining. So what is actually happening is I'm gonna edit this one, and I'm gonna go to my differences, and is this difference between pressure and C1. So is this one here. So now you can start to see that actually when I have a change in the pressure, I had, when this was not stable, my yield was actually really slow, really low, sorry. So it turns out that what it happened to be noise is actually a big contribution to the model. So before you go ahead and you start to clean, think about what you care. Because I didn't care about the model to explain the yield over the years. I care what happens day to day in the plant. If you want to do a planification of the production for years, yes, you want to do a forecast of that. But for explanatory, really think about what you're trying to achieve here. What are you asking the model? Are you asking the yield over time? So it will only find long trends, but it will not find things that are happening in the short term. And this is very important, because this is something that should come from the experts, from the process, from process engineers, from scientists in the plant, and not from the data scientists, because data scientists will help you with these tools, or as you can see, you can do it by yourself. So now we have, let's say we finalize, we have seen there is some collinearity, but and we can do this penalization methods. But for this demonstration, we're going to use these three methods here, these three inputs for the most famous modeling technique out there, which are neural networks. So for neural networks, I will put my inputs here, and I will put my yield here. And for the moment, I will just click OK. I will not add any noise, because here is a more flexible model to explain what is happening. And then I will, you can see this is the interface of neural networks for Jump Pro. But in normal Jump, as I've been using only here features that are in Jump only. So now you can, in Jump Pro, you will see that there you have several options. You can have a hyperbolic tangent activation function, a linear or Gaussian function. You can select the number of nodes in each layer. And you can see here that automatically in Jump, the penalized method is either in both versions, Jump and Jump Pro, is the square version. So you will penalize all of the methods automatically, and you can select, if you have Jump Pro, different penalization methods. So here the validation method by default is a holdback, so 33% of the data will be used for the validation. And then I have a model with this R square. I can change. So a good thing to do always is to just try a simple linear model to make sure that the linear model will not do a good job, and then you can start to add more complexity. So I'm going to add perhaps 3 and 3. It doesn't change much between these two. I'm going to add, yes, 5 and 5. Let's see if this goes any better. So this one is a little bit better, and I'm saying better because I see the R square here. So for the moment, and at the end, I will talk about at the end, which is in 5 minutes, I will talk about the validation. I will show you the diagram of what I'm doing here. This is fantastic. We have a neural network, which is something super fancy. Now, how can you explain what a neural network is doing? Well, you can take a look on the weights of the equation. You can take a look if you want in JUMP. You can also take a look of the equation here. You have a linear transformation inside of a nonlinear function, which is the hyperbola tangent, this n times by the nodes, and then you combine them together. But this is actually difficult to understand. But you can put it, if the model is good, wherever you want. But in JUMP, the biggest feature is the profiler. Anytime you do a model in JUMP, you have something interactive to show. So to explain this, it's better to go back to my plot, and you can see. Let's take a look. This is the yield predicted by my model, and this is the temperature one. So as I said before, temperature one goes go here from here. You will see that there is this kind of shape from lower to high and lower again, which is what we're seeing here. But I can play with that individually. Here, in this case, I have only a few dimensions to look at, so we can compare them. Flow C1 has the same shape, but you can see that the shape of the others change as I'm changing one of them, because this is a nonlinear system. So when I am in temperature 150, which is around here, my shape for flow C1 is changing. And you can see that right here. Not only that, but you can also do a simulation. You can simulate this. Let's say that what I'm looking at this is that this is actually impacting. So when the difference in pressure is really not well controlled, I have a problem. So I'm gonna add just a distribution of my difference in pressure, because this is a perturbation, and I can see what is the impact of the distribution of my yield here with that distribution of my pressure. So my recommendation in this case will be try to control your pressure and put the temperatures where the model says it's best, which is in this area. These recommendations actually can be done as well in JUMP. I can do a maximization of the problem, and I will say put the temperatures at 134, 320 for the flow C1, and then obviously keep this value near to 0. So I'm not only looking at this on the abstract way with these things that is difficult to explain, but I can interact with this, and actually I can recommend the best set points right away. So we almost done, and I was not making emphasis on something which is very, very important anytime we want to do a model, which is the main trick we use in data science. The main trick is these models are really, really flexible, especially neural networks. They can fit everything you want, and therefore they're prone to do what is called overfitting. You are familiar with overfitting. Is the problem of having, for example, a very high order polynomial. So if you have a very high order polynomial or a very complex network, like here, I can add a really, really crazy neural network, and I will get always a better model. So what is stopping me to get something that is overfit or not is this validation. But actually, if you have JUMP Pro, you can add you have to think about your data. So I said in the beginning, these data points are actually, it can be thought as independent one day to the other, because there's enough time between them and they are more or less stable. So I'm not modeling dynamics, I'm modeling more the static part of the system. And the random validation that was done by default in JUMP was working great. But if you have a problem where the system has higher autocorrelation, so for look at that, you only need to go to screening, to specialized modeling, and go time series, and you look at your yield over time. So here you can see my autocorrelation. It's not as important, especially partial autocorrelation. What that means is the yield can be explained by other factors, but not by how was my yield before, which in other words is, if I am sampling very high in milliseconds, the system is basically the same. So what explains my system is not neither the flow, neither the temperature, but how I was milliseconds before. So this is a sanity check. You have to look into the autocorrelation. And if you have a lot of autocorrelation, the best way to do is a time split. So you go to analyze in Jump Pro, you say, I want to do a validation column. I want to do this validation column by I want to have not only validation, but also a test. I will click go, and I will create a new column, which is a validation, which I can directly use in any of my models. I can directly use in a partition tree. I can put my validation right here, or I can put it in the neural network. Any model in Jump has the access to specifically decide what is the validation you want to add. And this is, again, this is the very important, because here I will use this data for modeling validation, and I will use this data set for the test. So this is not used any moment in the model. In machine learning, you know, this is for fitting, this is to avoid overfitting, and this is to test that the model is running. So in this case, it will be like, if I have my model in this data set, in this part of the data, in the moment of time, what will be my prediction? What will be how well my model will fit? So I just will show that. I put the validation there, and now I put this one, and then I have three different models. Okay, I have 3 different data sets, so I can see that this is actually not a good model for the test period I'm selecting. And we can talk about that in the questions. So that's all from my side. I need to thank Kevin Dunn, which is the author of the data set, which I adapted to this demo. And you have some resources there as well from the question before. And from that, if you have any questions, I'm happy to answer them.
Thank you very much, Francisco. That was a fascinating insight into the sorts of things that we can achieve with Jump. And speaking of Jump, a few of the questions that have come in have been very specifically about the software, and maybe there'd be some examples beyond the sorts of things that Solvay encounters. So I'd like to also invite and introduce Bernd Heinen, who is a JMP systems engineer. So he will be able to hopefully answer some of the questions that Francisco might not be able to do. So Bernd, just to check that you're with us, thank you for joining us.
Yeah, thank you very much. I'm here and I'm listening, and thank you, Francisco, for this wonderful presentation.
So first of all, hopefully a quick and easy one. This is from Guido, who says, can I export all of the graphs that I obtained from Jump? So can we actually export these reports in a way that we can share easily?
Yes, that is. Yeah.
Yes, go ahead, and I will show it while you speak.
Okay, yeah, good. Yeah, you show it. It's pretty easy. You can copy paste it to any kind of software, and you can also save the whole report in a variety of formats, including all kinds of graphical formats, but also like PowerPoint or HTML. And if you don't mind to put your data behind in an HTML document, you can even conserve the interactivity that Jump has.
So that would mean you could essentially, maybe on your internal network, you could have a real-time report, realistically, that shows the latest data you've got.
Not really real time, because Jump is an analytical tool, and we do not, on purpose, we do not hook up onto data sources so that a change in the data source would be immediately reflected in Jump. As you have seen Francisco going through an analysis, this takes some time. It will not be advisable to update the data in between. So, but you can save all these as a script, for example, and then run this script so that at decent times you have an updated graph, and you can see what Francisco's just showing, that even in an HTML report you have some interactivity left.
Yeah, so what we do in Solvay is we provide this. This is a website, so you don't need Jump to open this. And this is an interactive report, so you can have mostly of all of the interactivity that is provided in Jump but for the HTML report. So this is very useful to share across the company.
And I believe there are some embedded examples of this in the JUMP web page as well, so you can actually start to explore the sorts of things that, again, I was talking about Phil Kay earlier, puts on jump.com in his blogs and so on. So thank you, Guido, for the question. We've had one from Sydney who says, the example we're currently looking at is based on a data set with a large number of runs. How many runs do you need as a threshold before doing this sort of analysis becomes actually viable?
So we are part of, so in the industrial end, so this is a very important question because usually we have these data sets in the historians, okay? So what we look in the beginning is that we have certain variability over time of what we have here. So we are on the side of, we have already variability to look at. But it's true that then when you start to do this, you see that you need more variability in your data set. And for that, one of the great things about JUMP is one of the best design of experiment software. So you can combine, your data set with a design of experiments. So what you have in your data set are experiments. And if you have a lack of data to fit any model, it will recommend you where to put the new points. That's the way I will do it. You combine DOE with the current data set. You have to know how good you are.
So DOE, this initial stage, will essentially tell you what measurements you need to make in order to then be able to get the sorts of analysis you need at the sort of the other end of JUMP, which is what we're looking at right now. So thank you very much. We have technically run out of time, but let's just run another question, which is sort of the mirror image of the last one. And this is from Alejandro, who says that the visualization interactivity in JUMP seems amazing. So I'm glad we've been able to show you that. Now, I agree, and I'm sure both of our speakers would agree as well. The question is, how much data is Francisco manipulating right now, and how much data is JUMP capable of dealing with? So I guess we're looking at thresholds, but at the other end.
So I can say that I've been using this for 3,000 tags, so 3,000 columns, and 2 years of data, and in interpolation of aggregation of 10 minutes or 1 hour. And so far, I haven't seen any problem in my laptop. I have a high-performance laptop. I don't have a Chromebook, but so far I haven't seen any problem from the side of the software. But maybe Bern has a better limitation. But in the practical way, I haven't seen any limitation.
We have seen Francisco working with all numerical data, and this, of course, of this data type JUMP can handle huge data sets with millions of rows and hundreds or thousands of columns. If then the data has more like categorical variables or text variables, then that will slow down the manipulation significantly. Technically, there is no real limitation. It all depends on the amount of memory that you are willing to spend or to put into your computer, and then you can make JUMP faster and capable of handling even more data.
So the limitations are based on your own hardware rather than the software itself.
Yes.
Excellent. Well, we really have run over time now, but what we'll do is any questions that we haven't had a chance to answer yet, we will send on to Bernd and Francisco, and they, if they have an answer for you or they can point you in the right direction, then I'm sure they'd be more than happy to drop you a line. So thank you to everybody for asking all of those excellent questions, and thank you for joining us throughout the webinar itself. It's been fascinating, and the number of questions and the variety of questions coming in clearly shows that it's ticked the right sort of boxes. We are doing a series of webinars with Jump. So if there is anything more that you'd like to see, any specific examples or any particular things you'd like to learn, please email cwwebinars@rsc.org and we'll have a chat with Jump. We'll try and find the right people to talk to you and to demonstrate the sorts of things that you guys really need to see. And I must reiterate Phil Kay's blogs on jump.com. If you'd like to know more about the capabilities and how to actually make the most of it, then Phil Kay's blogs are an excellent resource, so that's well worth a look. But that is all we have time for. Thank you for sticking with us, even though we overran a little bit. I'm Ben Valsler, digital editor of Chemistry World. I have to thank Jump once again for helping us to find the right people and for supporting this series of webinars. A great big thank you to Francisco Navarro from Solvay, who has done an excellent job over the last hour. And thank you to Bert Heinen for joining us just for the last few minutes to take in your questions. So once again, drop us a line, cwwebinars@rsc.org, with any other things you'd like to know more about. And I hope to see you in the next Chemistry World webinar.